Okay. All right. Thank you, everybody. Great conference. And part of the evidence is me losing my voice a little bit over the last 3 days. Amazing conversations. So you guys must be thinking, yet another reliability talk. But trust me, our customers are telling us this is very important. So every minute of it is worth it. So my partner in crime, Oriol, and a key contributor here, our expert chemist, Benjamin Greenwood is here. So we'd love to have conversations afterwards if you guys are interested. So immersion is obviously holding a lot of promise. And when Micron entered this foray 2 years ago, we saw this amazing amount of innovation happening all over the place. But what we are hearing from our customers was something different. Our customers were telling us, hey, do you stand behind this, right? Do you really believe in this? All these developments from grounds up, grassroots is great, but I need somebody to back this up. So that's really where Micron came into the picture and said, okay, we're going to hear our customers' voice and be the bridge between this innovation and adoption. So that was our calling, so to speak, and we've been working towards that over the last 2 years. We are governed by standards. JEDEC is our friend in the memory industry, and OCP and JEDEC really complement each other in terms of standards. JEDEC being the component level and OCP systems. So we see those two as very comprehensive and complementary, like I said. But we also have a bunch of other standards we need to work by. And we're going to have a call to action for the team to support us. There are places where a lot of other standards have to evolve and support the immersion evolution and adoption. So some of this you've seen before, but I hope I can bring a new perspective in terms of why every bit of this is useful and important. We call this orthogonal stress domains because they all bring a unique perspective to reliability. And by nature of the word orthogonal, they are not dependent on each other. So we're getting secular pieces of information that all add up and reduce the reliability risk. So we went in with a holistic view of how we can look at it in a more comprehensive way. And bits and pieces of this has been done in different places, and sometimes all of them have been done. And in that sense, this is a repeat, but thinking of it, again, like I said, holistically brings a new perspective. So we hope to share that view and invite collaboration and development further. So we focused on thermomechanical, thermochemical, chemical, and environment. And each of these bring a very unique value add to our workflow. So with that, I'll hand over to Oriol and talk about the first one. Go ahead, Oriol.
Thank you, Rash. My name is Oriol. I'm a technical alliance manager at Submer, and I'm going to go through a bit about the reliability test setup that we have done for this qualification with Micron and the memory DIMMs. What you can see in the image here is the systems that we choose. Those were immersion-ready ASUS servers, 3 nodes with double CPU and the memory DIMMs, 48 Micron DDR5 memory DIMMs. So the test setup that we set here for the testing was fluid selection of PaO2 from Submer's perspective and in our deployments, as exception from South Korea and Japan, we tried to use low viscosity fluids, PaO2, GTL fluids as well with a low viscosity like the S5LV, some other fluids that give a very good performance to relieve the thermal properties from each chip in the server. So in this case, it was a PaO2 viscosity, a hydrocarbon fluid, and the system configuration was a 3 ASUS Hypertech, as I said, with 2 Intel CPUs and the memory DIMMs. Next slide. So the way that Submer is testing different elements to qualify those for immersion in our tanks, it's basically in three main stages, right? There is the initial stage, which is the material compatibility. This is where our fluid partners are taking most of the responsibility. There is, as you know, an OCP material compatibility list, which is already published for hydrocarbon fluids, which is focusing on which sort of plastics, sort of elements are a risk in the single-phase immersion fluids, which others not, and which others are not known, so we can test them if necessary. But here, after that main basic step, we are focusing on the aging of the component, when it will fail. Do we have an MTBF that we can trust? We can sell this with no risk and provide warranty on that. So basically, we do an aging testing. There is a formula that is used in the industry, very easy, and actually can change a few elements on it. But basically, at Submer, we can replicate every year of a component aging with 46 days at certain temperatures and at certain flow rates in our tanks. So here with the Micron memory and the ASUS servers, we just run the aging testing for 3 years. So as you can see in the picture, the first part is a reference performance test where we see which is the full throughput of the server that is working in immersion. Then we run 46 days of aging. We collect a fluid sample to see if fluid has any contamination, any bad situation because of the server, because of the fluid itself. We analyze that, and then we continue with another performance test to see if after the first year there is a performance degradation of that server, of that memory. If it remains the same, we continue to the second year, and like that until finally the third year. So at the end, we can see if after the 3 years there was any performance reduction on the server and on the memory, and therefore if also there was any affection to the fluid analysis after every year. If everything is okay, if everything remains the same, we are safe to provide a good environment, a warranty, and to be sure that it will be safe in production for any data center, right? So as I was mentioning, then there is the other one, which is the performance testing. As you may know, in the single-phase immersion tanks, you can have different temperatures of operation for the fluids. One of the benefits of immersion is that we can probably work at high temperatures, and this is very attractive to the customers, so they can reduce the power consumption for the cooling of the water that we require. So this is a very important test because here, with that graphic, we can understand which is the sweet spot where the server can work, which is the spot where the throttling is just going to happen. So we can work maybe 5 Celsius below that sweet spot and be sure to work on the most efficient temperature at the time that we are not damaging the server in most of the cases. So here is the other test that we have been doing where, sorry, Raj, can you go just one by one? Yeah, so here in that test, we are starting, for example, at 45 Celsius, we stress it, there is no throttling, we go 5 more to 50, we stress it, then 55, and we end up at 60, which is the maximum that we are allowing at the moment in single-phase immersion tanks from Submer. So then we do a cool down and a stress hardware to see as well which is the sweet spot. So in these cases, we figured out that the servers were able to work fine at 55 Celsius, which is a very good, efficient temperature for this, and that the memory was keeping up pretty well. So as a summary, here we have just the formula I was mentioning before and how we're calculating it at Submer. In our case, we use, as I say, 46 days at 70 Celsius. This is a high temperature. We are sometimes eventually before checking if there is any capacitors, any element that can be breaking down at that temperature. Initially, the aging test, the server is not in operation. It's just to check which is the oxidation of the components, which is the aging of them, to see if they are going to fail, but they are not in need to be in operation necessarily. So this test is a risky test, but it's made in a very controlled scenario, in a very controlled environment with plenty of sensors, of thermocouples, so we can check if at any point there is a component throttling. For example, in the ASUS servers, we found out that the VRMs, the voltage regulation modules, were throttling the CPU and not the CPU itself. So a small heat sinks with a small thermal interface materials were important to be added. From the fluid perspective, we are also doing analysis. There is many indicators that can tell us that the fluid is not okay, that is losing its properties or the dielectric capabilities. For example, the color sometimes is an indicator and sometimes not. You can be looking at a fluid that is a yellowish color, so it's a bit oxidated, but it can be perfectly working fine, so it has no risk in its capabilities in immersion. But then there is other ones that are, when we go to a real analysis into the lab, that if, for example, the breakdown voltage goes down, this is a very high risk element because then the electric fluid is losing its capability to do not conduct electricity in immersion. The resistivity and also the other, the dissipation factor are very important elements. So as you can see in this graphic, after all of the different testings and after the 3 years, there is no any samples of the fluid that reached any of the critical values to consider the fluid was in bad shape or it was a risk for the operation.
Okay, thanks, Oriol.
Sure.
So moving on, the chemical analysis part, we used what's been talked about earlier and then some more. As an example, not to go into too many details, but it's important for every component supplier to understand where they stand. And in that vein, here's an example using LCMS, liquid chromatography. We were able to characterize that our products, how they performed in isolation versus the overall system, and quite a bit difference, right? So in essence, we are able to fingerprint our product's performance in any system and be able to compare that to the system as a whole. So eventually, in case of root cause finding analysis, we're able to isolate the real source of contamination, et cetera. So I think in broad scope of deployments, this is very important to be able to isolate root cause and liability. And then finally, the thermomechanical stresses. As I said, we're governed by JEDEC, and we have to follow a rigorous set of tests that are designed for air cooling. So applying all of those to immersion, as some other presenters mentioned previously, works very well. And it gives us an extra hammer test, if you will, to go beyond the standard methods. So all that worked out very well in this case. Our products are really robust and hold up the aging and the lifetime test very, very robustly. Okay, so moving on. Finally, the warranty framework that I alluded to earlier, it's really net outcome, the net endpoint of all the work in many domains, right? After a lot of all this work is really, we can stand behind and say, hey, we feel good about immersion for our products. So in this case, memory performance, fluid stability, compatibility, and then thermal stability really give us the confidence to stand behind and say, okay, we have a warranty framework. So with this fluid, as an example, we have done that work. We feel good about it, and we invite the community to take this with a degree of confidence, and we invite to participate in more fluid systems and server systems, and take this to a logical conclusion. So with that, I'd like to say great progress by the OCP community. We need to make continued progress in multiple domains. Some are focused more than others so far, and we need to make progress on all fronts. We should continue to contribute to the base specifications with pros and cons, and that work group is super important. Special call out to integrators. So as I showed here earlier, having some kind of a fingerprint for each contributing product is going to be immensely helpful, we feel. And that can be the catalyst in my mind to take this to adoption levels. So really encourage integrators to help bring that to the ecosystem. We also need to pool the industry data to validate failure modes and be able to establish acceleration factors. So far, we have seen some from the coarse components, we probably need to find out more from every component. And then finally, we are governed by other standards for things like product labels, et cetera, and those are not very compatible with immersion. So this is a call out to the community dealing with standards bodies to find alternatives to things like product labels, which are really regulated. All right, I think that's going to do it for us, unless we have questions. I think we have a minute. Yes, please.
So, would you find some? Please walk over to the microphone so it's recorded. So, you define some success criteria in terms of resistivity. I saw your in your table, it was higher than 10 mega ohm. And the fluid that you used was a polyalpha olefin. Is this a general rule for all of the fluids or just for the hydrocarbon that you use?
Oriol, you want to address?
Yeah, that's actually a very chemical good question. I hope that Ruma, my colleague here, will be to help on that matter. I can tell that, of course, there is different type of fluids. I think for GTLs or esters, there is other tables. So for polyolefin, it's actually like that. I think actually those tables are the same that are defined in the OCP range of acceptation, when you have like the dielectric strength, the decay, the one that you just mentioned now as well. So all of those are references that Submer also at the very beginning created. Peter Cooper, which was our PhD, and helped sharing that with the community. So we're just following the standards that have already met by the, let's say, here in the industry to commit to those safety elements. But yeah, I mean, these are the ranges that we have so far today, and we are trying to keep those in our evaluations and testings.
Okay, thank you.
Thank you, everyone, by the way.
Okay, thanks.